Okay guys, welcome to another episode of Cuda Education. Today I want to discuss just a small part of the hit shader. Okay, so remember guys, we're at this stage, we're in the ray tracing glTF. We're in the ray tracing glTF project, and we basically have a glTF object and we're shooting primary rays into the scene. But I learned a couple things today. So I'm going to share it with you and sort of give you, give you sort of, a little bit more intimate knowledge of computer graphics, right? So look at this image and you could see it fairly clearly. You could see it fairly clearly, right? Things look pretty high def, right? Pretty realistic for the most part, right? And it looks good. It would pass if this was in a video game. It would get high marks for, just the visual detail and all of that good stuff, right? Okay. So what I'm going to do is we are in the glTF example, and we're in the closest hit shader, right? So this is the closest hit shader. So what I'm going to do is I'm simply going to I'm going to comment out, any kind of occlusion. All right. So you guys know that when I update a shader, these are the shaders, right? The GLSL shaders. When I update the shaders, I have to recompile, right? I'm not modifying the source code, even though in the source code you have to rebuild, but I have to recompile the shaders. It takes me a little while because I'm doing it for the whole thing. I really should update it so it just does it for this file, but I'll just leave it as it is, right? So I have to recompile the shader into sphere V format, SPIR-V format. That is a proprietary Chronos group format to ensure consistent interpretation of instructions across all GPU vendors. So the shaders are compiled into sphere V to make sure that there's no funny business when, a game ships and is being used and what have you, right? So we're gonna rerun our example now, and you're going to see that things look a little bit more pasty, right? It doesn't have that visual dexterity and detail that we once saw. Okay. You could even look at the straps and stuff. It just doesn't, it's kind of off, right? It's hard to really put it in words why it's off, but we know that it's off. Okay. It's not as good. Now, if you gave someone this in, 10, 20, 30 years ago, they would be like, wow, what is this? But we have seen better in 2025, right? So you could see that, something is just off, right? And this really cued me into something about sort of computer graphics, right? So we have I'll let me while I'm doing that, let me just I'll just take it back out and recompile. You know, but while we're looking at that, I'll just, you know, but we can see that, you know, something is off. The lighting just isn't there. Especially the thing right here, the oxygen mask. It's kind of pasty. You know, it's just not it's not the real deal, right? So there's a sort of fall off in the graphic quality. Okay, and this is what you know, everything is like solidly illuminated. Everything is consistently illuminated. There's nothing that's like, you know, no creases, no shadows, no like, you know, minor absence of light or anything. Everything is just purely and completely and fully illuminated, right? And this is a problem. Now, when we go back, so when we go back now, so now I've taken out the ambient, I've put back in the ambient occlusion stuff, and now we're running our example again, right? And when we run our example, we're back to, you know, more realistic, you know, it's more rich. There's more definition. There's, you know, slight, you know, we can see the straps are, you know, it's better. The mask is a little bit more, you know, put together and stuff. And this is basically what ambient occlusion is, right? So it's a cheap approximation of global illumination. Parts of the surface where you have, you know, tucked in stuff or creases or like, you know, corners or gaps or anything like that, you try to simulate them receiving less light, right? Because the lighting is now being affected by the environment around it, right? So, you know, you could see sort of there's a little bit more dexterity. I just like to use that word, even though it might not make sense, but you know, there's more depth to the the image, and it looks more realistic as a result. Now this is done here. It's artificially done because it has like there's a sort of a process, like extra images and stuff that sort of simulates the ambient occlusion for this example. And the reason you might ask is like, well, why would you have to simulate it if this is a ray tracing example? Well, for this particular example, we just shoot one primary ray, right? So we shoot one primary ray into the scene, and we don't really deal with secondary rays or shadow rays. You know, we just shoot one primary ray, see what happens to that ray, and then that's it. You know what I mean? So it's you know, it's not going to generate it itself, right? Not for this example, right? The purpose of this example was really just to, you know, process and deal with, you know, a glTF object, right? So secondary, tertiary, all of that stuff, it's not gonna show, right? Now, the thing is that if we go to, just real quickly, I'm gonna jump to this example. Oh, let me turn this off first. I'm going to jump to this example. This is a ray tracing reflections. In the ray tracing reflections example, we have multiple reflections, right? So this is true ray tracing because we have multiple reflections. We have reflections on the teapot, we have reflections on the floor, we have reflections of the reflection, all that stuff here. I mean, I did it in the previous example, but I think we limited the number of reflections to like 2 or 3 or something, or 4. I don't know. Right? But the more reflections is the more deeper you see the reflections of the reflections and all that stuff, right? So this example was, you know, we're really going in depth, right? But for our for this for the ray tracing glTF, it's just a primary ray, right? So we just have a primary ray. Now the thing is that so we're back to this guy again, right? So we have our full occlusion. I'm inclined, because now I'm paying more attention to it, I'm inclined to I am inclined to go back to take out back the occlusion to see what happens. So while I wait for that, we will hang out a bit. The other thing to notice is just like we have a geometry node and there's a geometry node and then a texture-based color associated with it, but I'll get into that in another video. And there's one more thing I want to cover in this video, but all right, so now let's do it without the occlusion, right? So we're back to not having the occlusion, and I really want to see, like, you see there's no shadows around the you know, the straps, right? There's nothing to say, hey, there's a strap here, so this, you know, what is beside the wire should have a shadow around it. Everything is just brightly illuminated, right? So again, everything looks pasty. You see, it doesn't have any illumination on it, right? So it just doesn't look as realistic as it could be with the occlusion, right? So let's, you know, just everything is just bright, everything is just illuminated, regardless of where it is or where the light source is. You know, there's nothing. So let me put it back. All right, and I have to recompile. All right, so the next thing that I want to discuss, so that's occlusion, right? And you know, at some point I'll get into the details of it, but you know, because of this example, I started to really investigate, like, you know, of the ray tracing examples, which one, you know, had the secondary and tertiary and the fourth and the fifth ray, so you could get like true path tracing stuff. And really it was only the reflections one that I could think of where, you know, you're truly following the path of all the you know, all the bounces, right? For the other ray tracing stuff, we're using the ray tracing API, we're using the ray tracing hardware, we're using the ray tracing functionality, but really we just care about the primary ray and then maybe a shadow ray. And actually in this example we do have the shadow functionality in it right now. the thing with this is it's very familiar territory, guys. Like we did this, we did the shadow stuff extensively. I even have a whiteboard video talking about shadows and all of the stuff. Notice that we have our trace ray ext, which now I learned is really a GLSL function, right? A shader language function to generate another ray. And we have our flags about what the instructions are for the shadow ray that is being generated, right? We have you know, dimensions for the light source. So where is the light source, right? That we're gonna use to simulate the shadow. So obviously, if the light source is in one location, a shadow is gonna be in a specific other location, and you know, vice versa. And then we have our hit value, right? We're always trying to update the hit value, right? And we know hit value was received in from the ray generation shader, right? The ray gen shader, right? So we're receiving hit value here, and I'm sure hit value was where is it? Right, hit value was originated here, right? So we broadcast this variable as part of the payload here, and then we receive it into this shader here. This is all on the GPU stuff, guys. This is all on the GPU. So we're working on the GPU based stuff, right? We're working on the GPU now. So yeah, let's just run it, right? So now we have shadows enabled, right? And we should see, yeah, we see sort of a shadow here. So here things are more illuminated, and here is the shadow. We see a shadow here and here. I think what we need to do is make it darker. So I think to make it darker, I lower the hit value thing. You know, guys, I gotta recompile, so don't complain about these videos being long. I gotta recompile, you know what I'm saying? I have to recompile. So I'm gonna try and make the shadow sharper, but familiar territory, guys. We've done this. This is nothing new. This is nothing new. It's the same. We assume that the scene is shadowed, and then we unshadow based on where it doesn't shadow, right? I mean, I wouldn't do it that way if I was designing the algorithm, but that's how the author of the code decides that he wants to do it, and I'll run with it, right? All right, so now let us see. We get a sharper shadow, right? So we could really see where, maybe even too sharp, but we could really see where the shadow falls, right? And if I simply move, if I move the light source, I'm hoping that, yeah, that should show a difference. If I move the light source, then the shadow will show differently, right? Because we're doing a ray test, and then we're launching a shadow ray to see whether at that point, going back to the light source, is it blocked, or does it reach the light source? If it reaches the light source, then it's unshadowed. If it doesn't reach the light source, then we know that particular pixel, that particular region, that particular area is shadowed. So let's run our algorithm again, and we're gonna see that, yeah, the shadow moved, right? So now it's, I guess this is where the light is, and then all of this right here is shadowed, and you could kind of see, you know, where the stick and even the tube, right? So I'm gonna re-comment out this, going back to original code. Need to make sure that things are back to the way we left them. So yeah, guys, so that is the occlusion, that is now I have a real world understanding of what it means to when they say ambient occlusion. There is also another thing called global illumination, which I'm sure is different from ambient occlusion. Right? I'm sure these computer graphics guys must be amazing at Scrabble. They have to be amazing at Scrabble because they just come up with all of these words, all of these names, all of these concepts. I would not want to play Scrabble with a computer graphics expert because they would win. Right? Let me make sure I'm back to where I was before. All right, so we're back to where I was before. We have our occlusion. We have, we don't have our shadow. We have the realistic looking stuff. The mask looks real. We have our shadows here. We could see we have our shadows, all that stuff, right? We could see through the goggles, all of that, right? Okay, so we're back to where we are. All right, guys, so this is it for now. Now, the occlusion side of it, how they sort of actually get it done is that there are a bunch of ancillary or extra files that I believe is used to sort of assist with knowing where a shadow normally would be, just based on geometry, or maybe they did do a full ray tracing thing and then they just said, okay, these are where the shadows are. Create a file that maps out where the shadows are and all of that stuff, like the minor shadows and the minor the changes in how much lighting you get based on the environment around where the object is and all that stuff. But I don't really want to get into it in this video. I just wanted to really talk about occlusion. Obviously quickly go over some kind of shadow stuff, but this is familiar territory. But just really talk about this occlusion stuff. It's doing an if statement. It's doing some math, and it's modifying the color variable, and then all of this work in here, well, basically all of this work in here is being transferred over to the hit value variable, right? And even the shadow stuff is being transferred to the hit value variable, right? So this hit value variable is really important. So remember, we start with the raygen hit value, right? And then it gets to the hit. When there's a hit, we make some modifications to the hit value variable, right? Here and here, if we comment it out, if we enable shadows, it would be here also, right? This is all this work is being done to get to an accurate value for the hit value. And that's pretty much it. But, we do this extra stuff because we want it to look realistic, right? But yeah, that's it, guys. Cuda education. If you guys want to join in, tutorial number 1 installs the Vulkan API on your Windows-based machine with a Vulkan-capable GPU and a ray tracing capable GPU. Tutorial number 13 installs all of these examples, right? So it has to be Vulkan capable. If you want to run the ray tracing stuff, you have to make sure your GPU is ray tracing capable. For NVIDIA, it's RTX and greater. Yeah, you guys heard, well, anyway, I don't even want to get into it. But yeah, I don't know about the others, AMD and Intel. And that's about it. Thank you for watching. Like, subscribe, get your friends to work on this stuff also. It is a great way if you have a commute to and from work, if you're on the train, if you're on the bus, if you are, anywhere, where you're basically sitting down for a long time, you could learn this stuff, right? If assuming that you're in a safe environment, you could work on it on your laptop. Just make sure the laptop has a capable GPU on it, right? You could work on it on your laptop, and usually your commute would disappear in no time because you're so busy learning about really, 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 really cool stuff like this. Did you guys hear that apparently Nvidia is going to invest in Intel? What do you guys think? How is it going to change things? Would love to hear your perspective on that stuff. You know, a lot of things are actually happening in computer graphics these days. You know, with all this AI stuff, just understand that, you know, AI can't show you or do anything that it hasn't seen before, right? So this is where creativity comes in, right? This is going to be your defense, is creativity, right? AI can't show or do, it's, you know, whatever it's being trained on, it's only what it's being trained on. It can't originate. I don't believe it can genuinely originate new stuff, right? So this is where your imagination and your creativity comes in, right? And this is where you know, this is where I think computer graphics will have a leg up, right, on all this stuff. But yes, the world is changing. Anyway, guys, thank you for watching. Have a great day.